Hello and welcome to Dove Biology, APES Lessons to Go. This is Unit 2, An Introduction to Matter. Now, as you may recall from your chemistry class, matter is defined as anything that has mass and takes up space. All matter is composed up of elements. Each element has a unique set of properties, and they can't be broken down into simpler substances through chemical means. Elements can exist as individual atoms. For example, neon. Or they might exist as molecules when you have two or more of that same element put together, as we have in diatomic oxygen. The oxygen that we breathe exists as two oxygens bonded together in a molecule. Now, if you have two or more different elements that are bonded together, they're going to be called compounds. Now, if those compounds are formed as a result of sharing of electrons in the valence shell or the outermost shell of those atoms, we're going to call that a covalent compound, as in water. But if instead those compounds are formed as a result of gaining or losing electrons in their valence shell, resulting in charged atoms held together by opposing charges, those are going to be called ionic compounds. Now, as we further examine these compounds, we can classify them as either being organic or inorganic. In order for a compound to be considered organic, it must contain carbon, bonded typically to other carbon atoms, and with various other atoms like hydrogen, nitrogen, or chlorine. All other compounds are going to be considered inorganic. Our simplest organic compound is going to be something like methane. Notice that it only contains carbon and hydrogen, which is our prerequisites. Glucose is another example of an organic compound. It has carbon and hydrogen along with oxygen. Another great example would be our chlorofluorocarbons. It is organic because it contains carbon and chlorine. In terms of important organic compounds that you'll need to know, there are four groups. The hydrocarbons are going to be the simplest organic compounds, containing only carbon and hydrogen, of which methane that we discussed earlier is a great example. A lot of our fossil fuels are hydrocarbons. Another one that you'll need to know are the chlorinated hydrocarbons. They must have carbon, hydrogen, and chlorine. A perfect example of that is the pesticide DDT. Next, you'll want to know chlorofluorocarbons, like we saw on the previous slide. A nice example of that is Freon 12, which was an important refrigerant that was used in the early days of chlorofluorocarbons. But as you may know, CFCs have been banned in the United States because of the role in depletion of the ozone layer. Lastly, but not leastly, you should refamiliarize yourself with those four important biological macromolecules: carbohydrates, proteins, lipids, and nucleic acids. The atoms, ions, and molecules that make up matter are found in three major physical states: solid, liquid, and gas. The change from one phase to another is typically the result of the addition or removal of heat. Now, there's a fourth stage of matter, which is called plasma, which is a high energy mixture of positively charged ions and negatively charged electrons. The sun and stars consist mostly of plasma. Now, scientists have made artificial plasma that's found in TV screens, gas discharge lasers, and in fluorescent lights that are above your head in your science class. Now, as with energy, we can classify matter based upon its usefulness. Matter can be classified as having high or low quality depending upon how useful it is to a resource. High quality matter is highly concentrated and easily extracted, whereas low quality matter is more widely dispersed and more difficult to extract. For example, the salt in a salt shaker is going to be highly concentrated and very useful to us, whereas the salt that's found in the ocean is more dispersed and less useful to us. The carbon that's found inside coal is highly concentrated and very useful as a fuel, whereas the carbon found in the exhaust is going to be more dispersed and less useful to us. Now, matter can change from one physical form to another, or it can change in its chemical composition. But when matter changes, either physically or chemically, no atoms are created or destroyed. This is known as the law of conservation of matter. For example, if we had a solution containing calcium chloride and sodium sulfate, we mix them together, a chemical reaction is going to take place. We would receive a white precipitate of calcium sulfate and table salt, sodium chloride. But in the process, no new atoms, no new matter would be created. That mass would be conserved. Matter can undergo various changes. In a physical change, the matter is going to change its physical form while maintaining its original chemical composition. For example, water. When it moves from its frozen form to its liquid form, and then to its gaseous form as vapor, it maintains its original chemical composition. It's still water. During a chemical change, we're going to have a chemical reaction where there's going to be a change in the arrangement of elements or compounds, resulting in something completely different than what we started off with. For example, if we take coal, which is pretty much solid carbon, and if we burn it in the presence of oxygen, we're going to produce carbon dioxide and release energy as a byproduct. In this case, our elements are going to be rearranged to form this new compound, carbon dioxide, that wasn't present before. But, as we said earlier, matter can't be created or destroyed, and so we see this conservation of matter in this chemical reaction. And many times, chemical reactions are represented as a chemical formula, which you should be familiar with from chemistry. In addition to physical and chemical changes, matter can also undergo nuclear changes, in which you have an unstable atomic nuclei that's going to emit ionizing radiation. Ionizing radiation is commonly used in energy production and medical applications. Unfortunately, exposure to ionizing radiation can cause genetic damage, as the high energy breaks the bonds that are in our DNA, and somatic damage, or damage to our bodily tissues. Pictured below, here we have some workers that are responding to the nuclear disaster in Chernobyl. They are quickly trying to place radioactive debris back on top of the core so that it can be sealed off. Unfortunately, as a result of their exposure, they received both tissue damage and genetic damage that oftentimes led to their untimely death. Now, these nuclear changes do happen naturally. It's called radioactive decay. Here, unstable isotopes will spontaneously emit fast-moving protons called alpha particles, or electrons called beta particles, or high-energy radiation known as gamma rays at a fixed rate. This rate of decay is called half-life, or the time needed for one half of that nuclei to decay to a different form of that isotope, which is called a daughter isotope. Now, each of these particles in the gamma rays differ greatly in their penetrating power. Alpha particles can be stopped by a piece of paper. Beta particles can be stopped by a block of pine wood, whereas gamma rays must be stopped by a much thicker piece of concrete. Knowing this allows us to construct systems for studying these particles or storing radioactive material. Other nuclear changes occur when unstable isotopes interact with other atoms or parts of atoms. In nuclear fission, certain isotopes that have a large mass number are split apart into lighter nuclei when they're struck by neutrons. This takes place often in nuclear power plants, where unstable uranium-235 is struck by a neutron, and then it sets off a chain reaction. And with each nuclear fission, each splitting of that unstable nuclei, it releases energy in the form of heat, which is then captured and turned into steam so that it would turn turbines and generate electricity. Another form of nuclear change would be fusion, which would happen in the sun or in neighboring stars. In fusion, we have two isotopes of light elements that are forced together at very, very high temperatures to form a heavier nucleus. For example, on the sun, we're going to have hydrogen 2 and hydrogen 3 fusing together at 100 millions degrees Celsius to form helium and a leftover neutron. And this generates a lot of energy. Now, ideally, we would like to do fusion here on planet Earth to be able to generate clean energy, but unfortunately, it takes a lot of temperature to make it useful for us to employ right now. Understanding the fundamentals of matter and its overall quality gets us one step closer to learning how to use our matter more efficiently so that we can have a more sustainable society.